All right. So I'm going to go through a quick concept that you're going to need for your AP Classroom questions that's going to pertain to the rest of the unit. So it has to do with finding work. So it turns out that we can also find work by looking at position or force versus position graphs. I suppose you could also call it a force versus displacement graph, right? That's kind of assuming that if initial position is counted as 0, position and displacement are really the same quantity. And this gives you the work done. So let's say we have a force acting over some displacement. It doesn't even matter what that graph looks like. If we want to find the work done by that force over this interval, all we would need to do would be to find the area underneath that graph. And that would give us the work done by that force on this object. Now, a couple assumptions that we're making. We're assuming that force is parallel to the displacement. And I suppose that you could also do this to find the total work done on an object if this graph was the total parallel force on that object. So let's go ahead and go through maybe 2 examples. So here we've got a situation, a 200 kilogram object experiencing a net force shown not to the right. I moved the picture around. It's over here now. So this is the net force on our object acting over some displacement. It's moving at an initial speed of 5 meters per second, and we're supposed to find the speed at 30 meters when it reaches that position. So if we want to do this, first thing we need to do is we need to think about the work energy theorem, which says that the total work done on our object should be equal to its change in kinetic energy. And the total work done on our object should be the area of that force versus position graph. And this should equal Kf minus Ki. And if we want to just kind of work out a little bit more, Kf is 1/2 mVf squared, and Ki is 1/2 mVi squared. And we are looking for Vf, so that's what we want to solve for. So I'm going to multiply both sides by 2 and divide both sides by m. We have 2 times area over m is equal to Vf squared minus Vi squared. So 2 times area over m minus we add Vi to this side squared is equal to Vf squared. And then we can square root both sides. We get something that looks like this. I hope I didn't make any mistakes. 2 times area over m. All right, so let's go ahead and work it out. So if we want to find the area of this thing, we have a box and a triangle. So for the box, we could do 100 times 20, which would give us 2,000. And for the triangle, we have 1/2 base times height. So that's 1/2, the base is 10, and the height is 100. So 1/2 times 10 times 100, so that's 5 times 100, which is equal to 500. These are all measured in joules, just to be really clear. So our area is 2,500 joules. That's the total amount of work done by this force. So I can do 2 times the total work done, which is the area, which is 2,500 joules. And then we want to divide by the mass of our object, which is 200 kilograms. And then we want to add the initial speed in, which was 5 meters per second squared right there. That should give us our Vf. And now I'm going to go ahead and plug that into my calculator. And this actually is 25 plus 25. So square root 50, and I hope I did this right. 7. that is not a very big change in velocity. Okay, so there we go. And I hope I didn't make a mistake. It seems like a pretty small increase in velocity. All right, so now let's go ahead and look at another example. So I want to do another one because I want to talk about what happens if the area is negative. So here we go. We have an object. They give us the initial kinetic energy, 20 joules. And wait, how much energy does it have at x equals 0? That's a typo. I meant to say how much energy does it have at x equals 10. There we go. They give us the initial kinetic energy of the object, and we're supposed to figure out how much it has at this point here. So if we want to do that for part A, we can use the work energy theorem again. And the work done, we would want to look only over that specific interval. So let's go ahead and just kind of break this up into different chunks, right? There's a triangle here, there's a box here, and there's a triangle here. And we want to find the area over each of those. So we do 1/2 base times height. So for the triangle, right, if we do 1/2 base times height, it's 1/2, the base is 5. Oh, I have my line tool going still. 1/2, the base is 5, the height is 20. So that's 1/2 times 5 times 20, which is 50 joules. This box is, what is it? It's 1, 2, 3 times 20, so 60 joules. And this triangle is 1/2 base, which is 2, times height, which is 20. So this is 1/2 times 2 times 20, which is 20. So the net work done over that interval is 50 plus 60 plus 20 joules. And let me just kind of double check that, right? 5. This one. Okay. All right, so that should be equal to delta K, and that's K final minus K initial. And the K initial we know is 20 joules. So the final kinetic energy is going to be 50 plus 60 plus 20. Let me just write that out. This is 130 right there. So that means 150 joules should equal our KF right there. So that is the energy it has at, right, this is specifically at x equals 10 meters. And the second part is asking for how much energy it has at x equals 15 meters. So you might not be surprised to hear that if we have a negative area, that will be negative work, which makes sense because here over this whole interval, the force is always acting in the negative direction, right? But the object is moving in the positive direction. So if the force is acting opposite the direction of motion, it should do negative work. So if we want to find out the work done here, we've got another triangle with a base of 5 and a height of 20. Right, so triangle would be 1/2 base times height, and that would be 50 joules. Yeah, 5 times 50 joules. So if we want to use the work energy theorem again, well, let's just think of the energy change from x equals 10 to x equals 15. So over that last interval, right, just over here, we use the work energy principle again, right? The total work done is equal to delta K. The total work done over that interval is 50 joules. And delta K is K final minus K initial. And K initial is the energy it had at 10, right? We're looking at this interval now. So we have 150 joules here. And that means the final kinetic energy will be, oh, this should be negative, right? Because that work done is negative. So we've got negative 50. No. We've got negative 50 plus 150 joules is equal to kF. So 100 joules is equal to kF. There we go. And this is at x equals 15 meters. All right, I hope this was helpful.